Imagine standing beneath a vast moonlit sky. The air is crisp, the stars endless, and somewhere in that infinite ocean of light, a question lingers. Are we truly alone? For decades, scientists, philosophers, and visionaries have pondered this mystery, yet the silence of the cosmos remains deafening. The numbers tell us extraterrestrial life should be abundant. Billions of stars, countless planets, endless opportunities for civilizations to rise. Tonight, we unravel the most compelling theories, the chilling possibilities, and the scientific enigmas that may explain the greatest mystery of our time. Why haven't they contacted us yet? The Drake equation. For many people who are interested in astronomy and the search for intelligent life beyond Earth, scientist Frank Drake's seemingly simple-looking formula from 1961 was the first real sign of scientific hope. Drake was getting ready for the first meeting ever about the possibility of talking to aliens at the time. He came up with this equation not as a final answer, but as an organized way to show the many factors that go into figuring out how many communicative societies there are in our world. At first look, this equation seems simple. It multiplies terms that show how fast stars form, how many stars have planets, how likely it is that life will emerge, and more. It led to a new era of studying the universe. It suggested that, at the very least, we might be able to figure out how likely it is that we will find friends who can send messages across interstellar space. The Drake equation is useful not because it finds a single magic number, but because it makes us think about what we think we know. How many new stars form each year in the Milky Way? What percentage of those stars have planetary systems? How many of those planets are in the habitable zone, and so on? All show how much we know or don't know about the universe. For decades, we didn't have any real information about most of these numbers. The best we could do was make informed guesses based on observations of only a few possible exoplanets and ideas about how life might start in certain situations. But thanks to projects like Kepler and TESS, we now know there are a lot more planets than we thought. And many of them are in areas where liquid water could, in theory, stay liquid. The change from guesswork to more and more evidence has sparked new arguments about whether intelligent life is more common than people thought. What has been hard to find is proof of that last part. The small number of these possibly habitable worlds where life actually changes to become smart, talkative, and persistent. We know it happened on Earth, but we don't know how often or how rarely it happens in other stars. The Drake equation allows for both of these extremes. Some people look at the numbers and think that the world is full of thousands of civilizations, while others make more realistic assumptions and come to the scary conclusion that humanity might be very much alone. In either case, it's a powerful reminder of how far away things are in the universe and how new our technology is for sending and receiving messages. Radio astronomy is only about 100 years old, which is a very short time in the big scheme of things. To make things even more complicated, it's hard to measure intelligence, and no one knows how long modern nations will last. Today we can see how fragile technology-based societies can be right here on Earth. Drake's last variable guesses how long a civilization can be found by looking at how well or how willingly it can send signs. If societies tend to break down or stop talking to each other, the time window during which they can be found might be small, making it less likely that we will ever cross signs in time. Each part of the Drake equation is a puzzle in its own right, showing us how much we still need to learn about life in the world and encouraging us to do more research. The rare Earth hypothesis. The rare Earth hypothesis is one of the most interesting ideas that has come out of the search for life in the universe. It was suggested by paleontologist Peter Ward and scientist Donald Brownlee, and it is much more careful than the hopeful predictions that the Drake equation led to. The Drake equation shows that the universe is full of possibilities, with billions of stars and countless planets that could support life. The rare Earth view, on the other hand, suggests that many cosmic events may have worked out just right to make complex life possible here on Earth. This point of view says that Earth's past and current environmental conditions may be so incredibly rare that it may be the only place in the world where complex organisms and intelligent life can be found. The first piece of the rare Earth puzzle is the sheer number of fortuitous factors that define our cosmic neighborhood. Take our Sun, for example. It's not merely a star of suitable size and type to support life on a habitable planet. It's also remarkably stable compared to other stars in its class, rarely producing massive flares that could sterilize a planet's surface. Our solar system itself is unusual in its arrangement. Jupiter, the gas giant, orbits far enough out that it serves as a cosmic shield against many comets and asteroids, yet not so far that it fails to intercept or deflect these roaming dangers. Meanwhile, Earth's orbit sits comfortably in the Goldilocks zone, where liquid water can persist over geological timescales without freezing solid or boiling away. Even the Moon plays a crucial role, stabilizing Earth's axial tilt and seasons, thus mitigating extreme climate fluctuations that might hinder the development of complex ecosystems. Then there is the changing inside of Earth. The surface of the Earth is constantly changing because of plate tectonics. This recycling of rocks and keeping the balance of gases in the atmosphere is important for life. Tectonic action also causes volcanism, which releases heat and important elements from deep inside the Earth. This helps with everything from making soil to the deep-sea geothermal vent systems that may have been the first place where life began. Ward and Brownlee say that every piece of this puzzle has to fit so perfectly that the rise of advanced life in other places might be very rare. Critics counter with the growing list of exoplanets, numbering in the thousands so far, found through telescopes like Kepler. While many of these worlds are uninhabitable gas giants or scorched by their stars, the sheer volume of discoveries hints that other Earth-like planets could lurk undiscovered. Furthermore, the definition of habitable continues to expand. The existence of extremophiles here on Earth, organisms thriving in acidic lakes, polar ice, or deep-sea vents, shows that life can cling to the most hostile conditions. Could other worlds support such resilient creatures? And if so, might these alien biospheres eventually spawn intelligent beings? Still, the rare Earth hypothesis says that while simple microbe life may exist in the universe, the change to multicellular, animal-like complexity may be incredibly rare. Earth's star, planetary order, moon, geological action, stable biosphere, and other features may be like winning the big prize in a cosmic draw. If that's the case, we could look for hundreds of years and only find empty rocks, gas giants, or worlds full of bacteria. In this light, Earth stands out as an incredibly unusual place where complexity and awareness can coexist. The zoo hypothesis. There are many ways that people have tried to make sense of the universe's apparent silence, but the zoo hypothesis stands out because it is both funny and scary at the same time. If no one waves back when we look around, it might not be because no one is there. Instead, it's possible that they're watching us from afar and staying hidden out of respect or even scientific interest. The zoo hypothesis says that powerful alien societies might be watching Earth in the same way that we watch animals in a zoo, in a planned, quiet way that doesn't get in the way of our normal activities. At first, this idea might sound more like science fiction than sober science. But in fact, it has a certain philosophical logic. If there are civilizations out there far older and more technologically sophisticated than we are, they may already know about Earth's developing biosphere. They might be waiting for humanity to reach certain benchmarks before making first contact, just as scientists might wait to approach a newly discovered primate species until it shows some level of tolerance or understanding. Proponents of the zoo hypothesis often reference a prime directive, borrowing from science fiction, which posits a moral or ethical code against interference with less advanced cultures. If aliens abide by such a code, they would have every reason to cloak their presence or confine their activities to subtle surveillance. Some people have thought that small, well-hidden probes could be hiding in our solar system and sending information back to a foreign network. Others wonder if things that seem natural, like fast radio bursts that can't be explained, or even strange geological events, could be indirect signs of observation. The main reason these ideas are not popular in the scientific world is that they are hard to test or disprove. The question is how to find a mind that is, by definition, set on staying hidden. Interestingly, this hypothesis also finds resonance in certain reported UFO or UAP sightings, with people suggesting that visitors could be performing field studies on Earth's ecology, or perhaps monitoring our technological progress. It's a leap, of course, and one that remains on the fringes of scientific discourse, but it underscores a common theme. Many individuals instinctively feel that our cosmic isolation might be illusory, that we may be subjects of a grand observation project intentionally kept in the dark until the time is right. The issue with the zoo hypothesis is that it's hard to see why powerful aliens would put their time and money into a strategy that is so long-term and doesn't involve them. Why would they want to watch us grow if that's their goal? To answer that question, supporters think that these watchers may have a very different view of time, in which hundreds of years or thousands of years of observation seem like a blink. Or they might just be interested in the natural development of intelligent species and study it for psychological or scientific reasons. Some people also say that advanced beings might do this for the sake of cosmic ethics. If their moral system values the independence of developing societies highly, then not interfering could be one of their guiding principles. Still, critics make a simple point. There is no direct proof for such a complicated galactic nature preserve. After all, if aliens were keeping such a close eye on us, we might expect slip-ups or other small signs now and then. Some people do think these slips happen because of UFOs, but there isn't any solid proof for it yet. In spite of this, the zoo hypothesis is still an interesting way to look at the Fermi paradox. Asking, why don't they show themselves, instead of where is everyone, changes the question. Perhaps they're watching us carefully, writing down every technical step we take and cultural shift we go through, until we are finally ready for a big reveal. The dark forest theory. One of the scarier ideas about why we haven't heard from aliens yet comes from a theory made famous by the Chinese science fiction author Liu Cixin in his trio of books called The Three-Body Problem, which is now a Netflix show. It's called The Dark Forest Theory because it says the world is like a dark forest full of hunters. When a society finds out about another, it has to decide whether to hide or attack. In this dark forest, telling everyone where you are is the same as putting a target on your back and asking an unknown enemy to kill you. The rationale behind this theory hinges on caution. In an environment of profound uncertainty, any civilization encountering another faces a question of survival. How can you know the other side's intentions? And if you don't know, how safe is it to allow them to live, especially if they possess advanced technology? According to dark forest logic, altruism and trust are luxuries too risky to indulge when resources are finite and the stakes are nothing short of existential. The safest strategy becomes remaining silent, concealing one's presence, and if necessary, neutralizing any threat before it can neutralize you. It's a jarring and a little scary change from more positive ideas of the universe as a possible society of friendly star travelers. The dark forest theory does, however, fit with a very real part of human nature. History is full of examples of societies at war, arms races, and preemptive strikes. Some people who believe this idea say that if intelligent alien life is like us, or at least faces similar stresses, then they may act in similarly protective or hostile ways. There would be a cosmic hush because mature societies would decide that any broadcast that shows where they are is a threat. Critics argue this perspective is too pessimistic, pointing out that a truly advanced civilization might also evolve morally, recognizing the benefits of cooperation over annihilation. Some also question the practicality of waging interstellar war in a universe where distances are measured in light years. After all, launching an attack at a star system thousands of years away involves enormous expenditures of resources and technology with uncertain returns. Moreover, by the time a strike reached its target, the landscape might have changed completely. It's possible that a civilization bent on conquest would consider it more trouble than it's worth unless they develop technologies well beyond our current imagination. A further issue to think about is whether or not it is even possible to hide forever. Societies need energy, and it's likely that more powerful societies use a lot of it. At that level of activity, they might leave behind techno signals that can be picked up in their star surroundings. Some experts say that if a society is advanced enough to hide all of these footprints, they might not be able to be told apart from the background noise of the universe, which would make the search very hard. So, the dark forest theory would say that the silence isn't because there isn't any life, but because many people have been hidden on purpose. The idea does, however, make us think about how we act. Radio waves, radar flashes, and other types of data have been sent into space by humans for many years. If the story about the dark forest is true, are we already screaming our presence into the void? Should these broadcasts be turned off so as not to draw attention to ourselves? The argument goes to places like METI, messaging extraterrestrial intelligence, where scientists and philosophers disagree on whether it's a good idea to send our location to people we don't know on purpose. Whether the dark forest theory turns out to be true or not, it brings up an important point about alien contact. We don't just wonder if they exist, we also wonder how they might see and react to us. Being careful might help you stay alive in a world full of unknowns. The Fermi paradox. After looking at ideas that aliens might be watching us, trying to hide from us, or just very uncommon, it's time to go back to the main puzzle that all of these ideas are based on, the Fermi paradox. It's named after the scientist Enrico Fermi and starts with what seems like a simple fact. The universe is very big, very old, and full of billions of stars. As a matter of logic, if intelligent civilizations are going to form, some of them should be able to get smart enough to move, talk, or leave clear signs of their presence. Why don't we see them then? The paradox is especially poignant when we realize how quickly a civilization, if unimpeded, could expand through the galaxy. Even limited to sublight speeds, probes could conceivably spread from star to star over a few million years. That might sound like an enormous span of time from our human perspective, but on the cosmic stage, it's a blink of an eye. By now, if aliens have been around for billions of years, one might imagine that some advanced species would have crisscrossed the Milky Way, leaving artifacts or signals in their wake. But as far as we can tell, the stars are still quiet. There have been no clear messages sent between stars, no solid proof of visiting spaceships, and no huge cosmic buildings blocking out starlight in a way that screams engineered. There are a lot of ways that the Fermi paradox feels more like a psychological debate than a simple question. It makes us question what we think we know about everyday life. Are we wrong? Is being smart less common than we think? Or is it possible that great societies move in ways that make them invisible, uninterested, or extinct? Some proposed resolutions focus on the notion that we're early bloomers. Life on Earth may have developed intelligence relatively quickly in cosmic terms. Perhaps the majority of habitable planets only recently evolved complex organisms, or they haven't had enough time yet for tool-making species to emerge and develop advanced technologies. Another branch of thought posits that intelligence may be self-limiting. As soon as a civilization acquires the capacity to mold its environment and to destroy itself, it hits a gauntlet of existential threats. Nuclear war, runaway artificial intelligence, ecological collapse, or other unforeseen perils could silence most species before they get a chance to travel the stars. There are also ideas that say we might be looking for the wrong signs. For example, the way we listen for radio messages might not work if an alien society has moved on to more advanced ways to talk that we haven't found yet. They might also use techniques that keep us from finding them, either to keep themselves safe or because their technology works in ways we can't see. All of these options show how the Fermi paradox leads to a lot of different kinds of thought. From an emotional perspective, the contradiction touches a nerve in the collective mind of mankind. But on the one hand, if we are really alone, It means that we carry the torch of cosmic awareness in a world that is silent. And if we're not alone and the universe is full of life, then the silence is an even bigger mystery. Are they trying to avoid us or keep us safe? Are we too young and simple for anyone to notice? There's something missing from all of these answers on their own. The Fermi paradox is still being talked about, and as our observational tools get better, it becomes even more important. Every new world found and every new cosmic event detected gives us more reason to believe that we'll one day find the undeniable mark of a mind from another planet. The Great Filter Theory. It says that somewhere along the line from simple chemicals to star-faring civilizations, there is at least one nearly insurmountable obstacle, or filter, that makes it much less likely that people will reach the advanced stages needed for contact and discovery between stars. This idea doesn't say for sure where the filter is, but it does help explain why the galaxy isn't full of civilizations that have left their mark. The path from non-living matter to a technologically advanced species involves many steps. The formation of a habitable planet, the emergence of life, abiogenesis, the development of complex multicellular organisms, the rise of intelligence, and the mastery of technology that can extend beyond a planet's surface. Each step might present its own difficulties. If any one of those hurdles is exceptionally rare or difficult to clear, then intelligent civilizations would be so sparse that they could effectively never cross paths. In that sense, the Great Filter could be an event or process so improbable that most, if not all, life forms stall out long before they start building radio transmitters or starships. The scary part of this idea comes when we think about whether people have already gotten past the Great Filter, or if it's still out there waiting for us. This could mean that the hardest steps, like the start of life itself, don't happen very often. In the event that starting a life is very hard, then we may already have beaten the chances by just existing. That would, unfortunately, make us one of the lucky few, which would explain the silence in space. Almost no other planet has been able to start living things. Instead, if the Great Filter rests in the future, it could be the problems with technology, society, or the environment that destroy civilizations once they are strong enough to change their surroundings. That could include nuclear war, climate change that gets worse over time, AI that gets out of hand, pandemics, or something else we haven't even thought of yet. If the Great Filter really is in our future, it makes it harder for people to stay alive in the long run. Maybe most societies that build advanced technology also come up with ways to destroy themselves. The idea that technology and intelligence might eventually destroy ourselves is a very frightening one. It would make sense why we haven't picked up any alien signals. Every culture that reaches the point where it can communicate with other stars quickly dies out before leaving a permanent mark on the sky. This may seem like a bad attitude, but it shows how the same traits that help us make progress quickly, curiosity, drive, and new ideas, can also put us at great risk of disaster. People who believe in the Great Filter hypothesis see every new science finding about how resilient life is as a sign that could tip the balance. For example, finding simple bugs on Mars or in the lakes of Europa could mean that life forms more easily than we thought. And if life comes about easily, then abiogenesis can't be the problem. It must be somewhere else. However, if we look deep into our solar system and don't find any signs of independent life, even in places that look like they could support life, then the building blocks of life may be less common than we thought, which would mean we have already gotten past the toughest obstacle. The idea of the Great Filter emphasizes how fragile and unique our situation is. We're not only looking for friends from other planets, we're also looking into our own future. If advanced life is really that rare, then that might be a sign of how dangerous the road ahead can be. At this point, no one knows for sure where or what the Great Filter is. Every new piece of information, from finding exoplanets to digging deeper into our solar system, gives us a new view. Self-destruction of civilizations. When we look at the stars and think about how quiet it is, the depressing thought comes to mind that many civilizations may start, but then die out because of their own actions before going very far beyond their home world. This idea, which is related to the Great Filter idea, says that technology isn't just a way to explore and communicate. It can also lead to disaster. Similar events in Earth's history show that growth can bring both hope and danger, though not on a cosmic scale. Take nuclear weapons, for example. Once humanity unlocked the secrets of the atomic nucleus, we gained the power to destroy ourselves many times over. Although we've never unleashed full-scale nuclear devastation, the potential for miscalculation, accidents, or the rise of extremist leadership remains an ever-present risk. This kind of threat isn't unique to nuclear weapons. The more advanced we become, the more intricate our technologies, and the more catastrophic they can be if misused. Artificial intelligence, synthetic biology, and climate-altering technologies all carry the potential for unintended consequences on a global scale. It's not hard to imagine that another species, a few steps or centuries ahead of us, might fall into similar pitfalls. Perhaps they develop ways to harvest massive amounts of energy but inadvertently destabilize their planet's ecosystem or unleash runaway AIs that treat biological life as a hindrance. Once technological reach surpasses a certain threshold, a single misguided experiment or power struggle might tip the balance. In a short time, that civilization could vanish from the cosmic stage, leaving behind no signals to mark its brief ascendancy. This idea isn't just based on thought about the end of the world. As part of the search for extraterrestrial intelligence, SETI, astronomers and astrophysicists have also thought about how long technological societies last. If it is true that species often find new, powerful technologies, but not often keep them safe for thousands of years, then not many advanced groups would be able to speak across interstellar distances. In a way, their broadcast window might only be open for a few hundred years, which is a very small amount of time in the grand scheme of things. By looking back at Earth's own history, we can see that there is more to the story. Throughout history, societies have come and gone many times, with resource loss, war, and disease sometimes putting an end to them. If these risks get worse as technology gets better, it's not hard to imagine whole worlds being destroyed by wars, natural disasters, or population losses. Unpredictability in social cohesion and governmental systems might not just be a human trait. It might be a universal trait. Life forms with competitive survival or tribal drives could keep getting in the way of their own peaceful growth. But everything isn't all bad. Not everyone will kill themselves, but it is a chance. If a society could see its dangerous road ahead of time, it could put in place strong defenses. Maybe advanced aliens that make it to space travel do so by putting aside their differences and building safe, united societies that understand how fragile life is. In fact, if we ever find signs from a really ancient society, it could mean that they stopped destroying themselves and found a balance that will last. So whenever we talk about why we haven't seen proof of advanced beings, the threat of self-destruction is always present. The lack of signals could be a quiet witness to many dead worlds, places that were once full of promise but were destroyed by their own actions. That being said, our task isn't just to find life beyond Earth. It's also to think about how we, as humans, can stay safe in the dangerous waters of fast technology growth without losing who we are. Cosmic timescales. While we think about the idea that alien societies might hide or destroy themselves, another idea shows how hard it would be to find them in the first place: the vastness of cosmic time. The age of our world is about 13.8 billion years, which is a very long time compared to the age of human society, or even the age of all life on Earth. At these sizes, civilizations might come and go like sparks on a cosmic campfire, barely touching each other in time. Imagine, for instance, a planet orbiting a star much older than our Sun. Life on that planet could have taken root billions of years ago, flourishing into intelligence, and then either transitioning to a higher plane of existence or succumbing to some disaster long before Earth's first primitive cells emerged. If their advanced era ended millions of years ago, we would see no trace of them now, unless they left behind structures durable enough to survive millennia of cosmic wear. On the flip side, a younger star system might just be getting started on its evolutionary journey. If advanced life has yet to appear there, we're effectively looking into a temporal vacuum. No signals, no footprints, simply because they haven't had enough time to evolve and start transmitting. When we think about how long stars actually last, things get even more complicated. Some stars burn out quickly and young, not giving life a chance to start for more than a few million years. Some, like red dwarfs, can last for tens or even hundreds of billions of years. This means that life could grow more slowly on their worlds. As a result, any society that forms on such a star could still be in its early stages of microbes by the time humans start exploring the galaxy. Alternatively, they could have arrived a long time ago if conditions were better. Time also matters for communication. When we detect a signal from a distant star, we're essentially looking backward. The signal could have taken thousands of years, or even longer, to get here. By the time we decode it, the civilization that sent it might have gone extinct or moved on from radio-based transmissions. Conversely, if we decide to send a message to a system many light years away, we must reconcile that any reply would arrive far beyond our own lifetimes. A back-and-forth conversation could, in principle, span multiple generations, requiring a sustained effort and a kind of communal patience that most human endeavors have never needed before. The concept of how societies move forward makes things even more complicated. When a species reaches a certain level of technology, they may quickly move beyond what we think of as society, possibly combining biology and technology, or changing to ways of living that are hard for us to identify. These huge changes can happen over hundreds of years or thousands of years, which is again a very small part of the age of the world as a whole. Big timescales, then, tell us that looking up at the sky with telescopes and radio dishes isn't the only way to find alien life. Being aware that we might be missing whole periods of action is also important. Throughout billions of years, societies may rise and fall. Earth's recorded past is only a few thousand years long, which means that our sense of growth is like a single page in a book about all the big events in the universe. If intelligent life is common, the silence might be because their clocks are set so far ahead of ours that they were awake or will be awake at times that are very different from ours. In this way, the world may be full of aliens with very different lifespans from our own short peak of rapid technical progress. We might get lucky and meet during a window when both of our civilizations are advanced enough to talk, close enough for signs to travel, and eager enough to reach out. Until then, the gap of ages is a barrier that is almost as strong as the distance itself. The case of interstellar distances. Assume you are on the beach and try to throw a grain of sand to a friend who is standing miles away. This silly picture gives you an idea of how hard it would be to move between stars and even talk to people in other stars. Just the distances between planets in our solar system can be mind-boggling. When you add hundreds, thousands, or millions of planets to the list, the numbers become almost impossible to understand. Proxima Centauri is more than 4 light-years away, which is more than 25 trillion miles. It is the nearest star to our Sun that is not our own. It would still take tens of thousands of years to get there, even if we had spaceships going as fast as the fastest spacecraft ever made. To get across these lengths in a reasonable amount of time, a society would need to understand and be able to change the laws of physics much more than we do now. Ideas like wormholes, warp drives, and hyperspace jumps are common in science fiction. Even though these ideas spark our imaginations, they are still just guesses based on what we know about science right now. In relativity theory, the speed of light is the fastest thing that we know of that can't move faster without breaking the rules of physics as we know them. And it takes an unthinkable amount of energy to move at or near the speed of light. Whether you're giving or receiving messages, light years are very far away. Radio waves moving at the speed of light need more than 4 years to reach the closest star. Our galaxy's core would take about 26,000 years to reach. A message sent back and forth could last the lives of many civilizations on Earth, given that anyone is still alive to receive a return. On cosmic scales, this delay makes it impossible to talk in real time. Rather than that, we have to send one-way messages into the dark and hope that someone will catch a bit of our broadcasting someday. The sheer magnitude of these distances adds layers to the Fermi paradox and related theories. It's not just about whether aliens exist or wish to communicate. It's also about how likely it is that messages could be exchanged in the face of such immense separations. A thriving civilization on the other side of the galaxy could be sending out signals right now, and we might only detect them many millennia from now, long after that civilization has evolved or disappeared. Conversely, we might be signaling into a cosmic void that won't answer back for just as long. Another great task is going these long distances by foot instead of by radio wave. One idea for an answer is generational ships, which would let people spend their whole lives traveling. A crew might set out on a trip not expecting to reach land. Instead, their heirs might end up in a star system that is very different from what they knew before the journey. For this kind of travel, you need more than just advanced technology. You also need to be able to keep your mind and culture stable for hundreds of years, or even thousands of years. There's also the question of whether super advanced civilizations would even need to travel in conventional ways. They might have developed alternative methods, maybe harnessing black holes or exotic particles to circumvent these limitations. Yet until we see evidence of such technology, we're left grappling with distances that dwarf anything in our practical experience. Even our solar system, vast as it is, becomes minuscule next to the trek to the nearest stars, let alone the broader galaxy. In the end, the lengths between stars are not only a technical problem, they are also a psychological one. They make us realize how small we are in the grand scheme of things and face the chance that even if life exists out there, we probably won't meet it in our short lives. Technological mismatch. When it comes to understanding a possible lack of contact from extraterrestrial civilizations, a critical yet sometimes overlooked angle is the concept of a technological mismatch. It's easy to assume that if another civilization exists, they'll communicate in ways we can recognize. Much like we presume someone from another country might still speak a language we can translate. But consider how quickly human technology has changed over just a few centuries. Our earliest electronic communications date back only about 100 years, cell phones and the internet a few decades. Extending this pace of change outward, it's plausible that an alien civilization could employ methods of communication so advanced or so different that we simply wouldn't identify them as signals. From our perspective, radio is the gold standard for scanning the skies, mainly because it's a low-energy, low-interference, long-distance medium. However, to a civilization much older, radio might be as antiquated as smoke signals are to us. They might rely on quantum entanglement for communication. Though current physics suggests entanglement cannot convey usable information faster than light, there could be workarounds or extensions of physics beyond what we know. They might communicate via neutrinos, gravity waves, or some exotic particles we haven't even discovered yet. These signals could pass through matter or remain outside the range of our existing detectors. We might be surrounded by an invisible tapestry of alien messages, while our technology picks up nothing but cosmic static. Encryption or compression is another thing that makes things harder. Advanced societies might still use electromagnetic waves, but they might encrypt or compress them in ways that make them fit in with the background noise. Our search methods usually look for structured or repeated patterns because we think that intelligence shows itself through clear signs. But if an alien data stream is so tightly packed or written so well, it could look like random noise. In this way, it's possible that we not only can't make similarly advanced signs, but we also can't tell them when they're coming straight at us. The fact that communication channels have changed so quickly in the past shows how temporary some channels can be. Often, technology changes so quickly that things that were common just a generation ago are no longer useful. In the 20th century, we sent signals into space that were weaker as they moved outward. These were the first TV and radio programs. Strong messages are also leaking less into space as we move toward digital and fiber optic systems. If we apply that to aliens, then maybe a society only leaves a trace electromagnetically for a short time before switching to safer or faster ways to send information. Then there's the chance of completely different feelings or ways of thinking about science. Aliens might not see or hear the way we do. Their DNA may have led them to create tools that can change dark matter or dark energy, which make up most of the universe's mass and energy. Our devices were made to find photons and other normal particles, so they wouldn't be able to pick up their signals. Not only space, but also what we think of as detectable could be used to measure the gap between us and them. We also struggle with the idea that the difference in technology might not just be because the aliens are more advanced, but because we are at a different stage than they are. They may be behind in some areas of science while being very good at others. As a result, two cultures have made tools that are very different from each other, like two ships passing in the night. Their instruments might not match up with ours in a way that lets both sides know the other is there. This is because our instruments are shaped by our past and environment. The Galactic Habitable Zone. For centuries, humanity's concept of a habitable zone centered on the distance of a planet from its star, the fabled Goldilocks band, where temperatures allow liquid water to persist. But as we've broadened our celestial perspective, astronomers have realized that habitability is also a galactic affair. The Milky Way is a vast spiral galaxy stretching over 100,000 light-years across, with a crowded core in the center and more tenuous outer regions. Where a star forms in this sprawling environment can drastically influence that star system's potential for life. A galactic habitable zone, GHZ concept, considers things like the amount of metal present, the frequency of supernovae, and the general safety of the environment. In astronomy, metallicity refers to elements heavier than hydrogen and helium, like carbon, oxygen, silicon, iron, and others. These elements are necessary for making hard worlds and complex chemistry. Usually, the metallicity is higher the closer you are to the center of the galaxy. This is because many stars have lived and died there over many generations, adding these stronger elements to the space between the stars. On the other hand, this busy area has more regular disasters like supernova blasts and maybe even gamma-ray bursts that can poison nearby worlds with radiation. Too close to the core, and the chances of life surviving repeated hits from space get lower. On the other hand, metal content drops dramatically in the galaxy outskirts, which are very far from the sun's path. If stars form there, they might not have enough heavy elements to build strong planetary systems. Or if they do build planets, they might not have enough of the important elements for complex biology and geology. The number of stars is also less dense, which can be both good and bad. It's possible that fewer supernovae means fewer events that wipe out whole species, but you also lose the chance meetings or gravity pulls that can stir up cosmic matter and lead to interesting evolutionary paths. Our own solar system sits somewhere in the galactic suburbs, roughly 26,000 light-years from the center. We benefit from a moderate amount of heavier elements, enough to form Earth and the other rocky planets. But we're also spared the brunt of the intense radiation storms that occasionally occur in the central regions. In essence, we might occupy a sweet spot where the chances of planet formation are solid and catastrophic wipeouts are relatively infrequent. This has allowed life on Earth billions of years of relatively stable development. Habitable doesn't always mean teeming with intelligent life, though. It only means that conditions aren't completely against life's basic chemistry and long-term development. On top of that, the GHZ's edges are not solid lines. Astronomers disagree on how wide or small it really is, and how it changes over time in the universe. Some say that early in the history of the galaxy, supernovae would have made large parts of space unusable for life. Others say that as stars and planets aged, some areas might become better for life to develop. The idea of a livable zone in the galaxy as a whole adds another layer to the Fermi paradox. Could it be that alien civilizations just gathered in certain parts of the Milky Way, and were on the edges? Or is it the other way around? If it's true that life is more likely to happen in some places, then advanced societies might not be spread out widely. It's even possible that many planetary systems are formed by star systems in high metallicity zones close to the center of the galaxy, but they keep getting hit by radiation bursts that stop life from becoming more complex. On the other hand, life may be more stable on the edges, but they are still so far apart that societies rarely meet. Different types of alien civilizations, Kardashev scale. Not all advanced societies are created equal, or so theorized Soviet astronomer Nikolai Kardashev in the 1960s. Looking at the prospects of civilizations that might be centuries or even eons ahead of ours, he devised a scale based on energy consumption and mastery. Type 1 harnesses the full energy potential of its home planet. Type 2 taps into the total energy output of its star, and Type 3 wields the power of its entire galaxy. While this framework is somewhat simplistic, it sparked a revolution in how we imagine a civilization's growth and capabilities. A Type 1 civilization would be something akin to a planetary powerhouse, controlling global resources, perhaps harnessing solar energy, geothermal power, or advanced nuclear fusion at such scales that energy scarcity effectively disappears. Humanity isn't there yet. Some estimates place us at around 0.7 on the Kardashev scale, given our current energy use. But even jumping to a full Type 1 status would transform human life. We'd be able to reshape weather patterns, avert natural disasters, and maybe even reach beyond our planet in a more sustainable manner. Type 2 steps up dramatically. Instead of relying on a single planet's resources, a Type 2 society captures the energy output of an entire star. One hypothetical mechanism for achieving this is a Dyson sphere, or a similar megastructure, that encases the star and extracts its energy. Building such a construct would require astronomical resources, likely involving asteroid mining, planetary disassembly, or other feats of engineering that currently reside in the realm of science fiction. However, if a civilization managed it, they'd have at their disposal enough power to fuel massive space fleets, conduct planet-scale engineering projects, or even undertake cosmic terraforming on nearby worlds. When we get to Type 3, we're dealing with something that makes no sense to humans, using energy from a galaxy with billions of stars. From our point of view, such a society would look like a god. Its power could reach across thousands of light years and change the way whole parts of the galaxy work for its own goals. One might think that if such powerful powers existed, it would be impossible to miss their marks. For example, they could build Dyson spheres around many stars, make fake worlds, or even use black holes to get energy. The growth of a Type 3 could create techno signatures that can be seen from very far away. Still, we've looked up at the sky and haven't found any solid proof of Dyson spheres or large-scale astroengineering yet. That absence makes me wonder. It might be much harder to get to Type 2 or Type 3 level than Kardashev thought. Civilizations could destroy themselves before they get there, stop growing because of changes in culture, or just lose the drive to do so. Another reason could be that these advanced societies have learned to hide or reduce the amount of energy they use. This has led to what is sometimes called a silent civilization that hides its presence to avoid drawing unwanted attention to itself. Others think that once a society has advanced technology, it won't need such large physical infrastructures and will be able to move into digital worlds or use energy in ways we haven't yet found. Kardashev's scale also presents a trap for our imaginations, since it relies heavily on a continuous growth model that might be distinctively human. Not all species might equate progress with greater energy consumption. Some could develop sustainable practices that keep them at a comfortable equilibrium. But the scale does serve as a simple scaffold for picturing how truly vast differences in development could exist between cosmic neighbors. When combined with the Fermi paradox, it nudges us to ask, if a Type 3 civilization ever emerged, why haven't we seen it, either through obvious astroengineering or through signals that dwarf our meager broadcasts? The Kardashev scale is an interesting way to show the different technological altitudes that a society could reach. As we keep looking, we need to keep in mind that even one rung off this ladder would mean a huge difference in skill levels. That gap could explain both the emptiness of space and the idea that, somewhere, an unimaginably advanced society has chosen a road we can't yet understand. This could be because, as they rise, they become less likely to show themselves to less powerful beings like us. Dyson spheres. There are many amazing ideas connected to the Kardashev scale, but Dyson spheres are one of the most interesting. Freeman Dyson, a mathematician and physicist, first wrote about the idea in a 1960 paper. The original idea wasn't necessarily about building a solid shell around a star, as some pictures show. Instead, it was about a swarm of energy-harvesting satellites orbiting so close together that they collect most of the star's light. At its heart, the goal is to capture a large portion, if not all, of a star's radiant energy. This would give a society power on a scale that is hard to imagine. Why would an advanced society want or need such a colossal structure? The simple answer is energy. As a species grows in technological sophistication, so does its appetite for power. Dyson realized that if humanity's energy needs continued to climb exponentially, eventually we might look beyond planetary resources to the full luminosity of the sun. He proposed that a star-encompassing swarm of solar collectors could supply energy far beyond anything Earth alone could offer. This notion fits elegantly with the idea of a Type 2 civilization on the Kardashev scale, one that controls the entire output of its star. Building a Dyson sphere, shell, or swarm is an engineering feat of cosmic proportions. The massive material needed to surround a star is staggering. Some theories suggest dismantling entire planets, especially rocky ones, might be required just to gather enough raw resources. The logistics of such an undertaking boggle the mind. It would involve advanced robotics, AI-driven mining operations, and a deep understanding of astrophysics to ensure stability. There's also a constant battle against orbital mechanics. Satellites must maintain positions that don't collide or drift out of the arrangement. In reality, most serious proposals lean toward a swarm rather than a solid shell, with countless interconnected platforms or mirrors forming a vast cloud-like array around the star. Dyson spheres, or swarms, are interesting to look at because we might be able to see them from across the galaxy if we know where to look. A star that is mostly hidden by a swarm would look less bright in visible light, but it could give off too much heat in the infrared range. Astronomers have thought that if foreign civilizations made these kinds of buildings, they might have sent out strange infrared signatures, which are energy leaking out as waste heat without meaning to. This way of thought led to the search for Dysonian SETI, in which scientists look for stars whose temperatures or light readings are off in ways that point to large-scale engineering. Some people say that even if a culture wanted to build a Dyson sphere, it could find better ways to do things. There may be advanced physics or energy management methods that we can't even imagine. In addition, a society that is truly no longer limited by resources might not even need huge buildings to store energy. Instead, they might figure out how to control quantum events or access energy at 0 points. Still, Dyson spheres are one of the most famous theoretical megaprojects. They are a way of thinking about the limits of a single world and the dream of using a whole star. Exoplanet discoveries. The power to find planets outside of our solar system, which we call exoplanets, may be the most important change in modern science. Not long ago, it seemed impossible to find planets around stars that are dozens or hundreds of light years away. But progress in making telescopes, analyzing data, and setting up observatories in space has made that dream a common science fact. We now know for sure that thousands of exoplanets exist, and thousands more are waiting in line to be proven. This list is growing quickly and gives us exciting hints about the different kinds of planetary systems that might be in our galaxy. The story of exoplanet discovery began in earnest in the mid-1990s, when astronomers detected a planet around the star 51 Pegasi. An observation that confirmed for the first time that stars like our Sun could indeed host their own planetary families. Initially, these findings puzzled theorists. Many of the first exoplanets found were so-called hot Jupiters, massive gas giants orbiting perilously close to their host stars, in stark contrast to our solar system's orderly structure, with small rocky planets near the Sun and gas giants farther out. The presence of these hot Jupiters hinted that planetary systems could form and evolve in ways we hadn't anticipated. Enter the Kepler Space Telescope, launched by NASA in 2009 with a singular mission: to stare at a small patch of sky and detect minute dips in starlight caused by planets passing in front of their stars. This method, known as the transit method, has proven remarkably effective. Whenever a planet crosses a star's face, it blocks a tiny fraction of the star's light. By measuring that dip and how often it repeats, astronomers can infer the planet's size and orbital period. With Kepler's observations and those of its successor TESS, transiting exoplanet survey satellite, we've uncovered a dazzling menagerie of planetary types: super-Earths, mini-Neptunes, lava worlds, water worlds, and more. The fact that there are so many planets is one of the most exciting things that these findings mean. We think there is at least one planet around almost every star in the sky. This new way of thinking about things has changed how people talk about life in other places, which has a direct effect on models like Drake's. If there is a lot of space on a world, there is a better chance that some of it might have conditions that are good for life. Some exoplanets, like those in the TRAPPIST-1 system, are in the habitable zone of their star, which makes people think they might have liquid water and be able to support life. We learn that Earth-sized doesn't always mean Earth-like, but it's still enough to make us wonder, could some of these faraway worlds have germs, trees, or even civilizations? That being said, finding a planet is only the beginning. The next task is to figure out what it is made of and how it feels. This is where spectroscopy comes in handy. Astronomers can find signs of chemicals like oxygen, carbon dioxide, methane, or water vapor by looking at the light that passes through or bounces off of a planet's atmosphere. Each possible biosignature increases the chance that biological processes are at work if it is proven. We are still in the early stages of analyzing the atmosphere, but projects like the James Webb Space Telescope are beginning to open the door. This means we may be able to find more subtle signs of life, or even techno signatures, such as industrial pollutants or patterns that have been changed in strange ways on other planets. Even with the progress, the distance barrier is still very high. Even a planet that looks so habitable might be hundreds or thousands of light years away, too far for any cosmic ship that will be built in the near future. But this flood of information about exoplanets has already changed the way we think. We no longer see our solar system as a unique gem in a sea of stars. Instead, we see ourselves as one of many planetary arrangements, each with its own possible stories of life and evolution. Extremophiles on Earth. It's easy to assume that life requires temperate climates, abundant sunshine, and mild chemical conditions, the sort of environment we associate with a lush garden or a calm ocean. Yet Earth's most resilient organisms often tell a different story. These hardy life forms, collectively known as extremophiles, thrive where we least expect it, in boiling hot springs, acidic pits, sub-zero glaciers, or deep-sea hydrothermal vents. Their very existence expands the definition of what is habitable, forcing us to re-evaluate our assumptions about the conditions in which life can take root and evolve. Think about thermophiles and hyperthermophiles, which are types of bacteria that live in hot springs in Yellowstone or deep below the ocean's rock. They have changed enzymes so that they stay stable at temperatures where most proteins in living things would break down. Or look at acidophiles. They do best in places where the pH level is so low that they can break down most metal. On the other hand, psychrophiles do very well in Antarctic ice because they have special proteins that keep their cells from freezing. Halophiles, on the other hand, like places that are very salty, like the Dead Sea or salt flats, where most living things would die of thirst in minutes. All of these cases show how amazingly different life can be, at least on Earth. For astrobiologists, extremophiles aren't just a curiosity, they're a beacon of possibility. Their adaptations suggest that if extraterrestrial environments are hostile by human standards, whether due to extreme temperatures, acidity, radiation, or pressure, life might still find a foothold. Consider the icy moons of the outer solar system, such as Europa or Enceladus. Beneath their thick crusts of ice lie salty oceans, heated by tidal forces. If terrestrial extremophiles can prosper in deep ocean vents heated by geothermal energy, then perhaps alien microorganisms could do something similar on these moons, using chemical gradients as energy sources instead of sunlight. Mars, with its thin atmosphere and extreme temperature swings, once seemed hopelessly barren, but the discovery of possible brine streaks and seasonal methane spikes raises the prospect that microbial life could persist underground or in temporary liquid water pockets. Even Venus, long written off as hellishly hot and corrosive, has attracted renewed interest. Some researchers speculate that extremophiles might inhabit the cooler cloud layers high above the planet's scorching surface, though that remains highly controversial. Still, the boldness of these ideas rests largely on what Earth's own extremophiles have taught us. Impossible environments can sometimes be anything but. Life's ability to change, develop, and take advantage of new niches shows how little we may really know about its potential to appear in other places. Scientists have thought about other planets for hundreds of years by comparing them to Earth. However, as we learn more about germs that can survive sulfuric acid or radiation levels that would kill people, our idea of what makes a place habitable expands. Even worlds that were once thought to be dead, like Titan, whose surface is full of liquid hydrocarbons instead of water, could be home to strange life forms that use chemistry that isn't known in terrestrial biology. Extremophiles also have an effect on how we look for life. We are no longer limited to looking for Earth-like signs in Earth-like settings. We know that biosignatures of life could come from metabolic pathways that are very different from those on Earth. So, the tools on rovers and orbiters are made to find tiny gases and organic molecules, even in places where the temperature or pH would kill most known living things. At the same time, theoretical work on strange biochemistry is adding more molecules to the list of molecules that we think show life. SETI and its search for signals. SETI, or the Search for Extraterrestrial Intelligence, is one of the most well-known science projects that tries to answer the question, are we alone? SETI's most basic task is to look into the sky for signs that might mean there are advanced civilizations there. In the past, this meant sorting through radio waves picked up by big antennas to find patterns that stand out from the background noise of space. Even though it's easy to explain the idea, putting it into practice is like trying to find a needle in a very large stack of haystacks. Modern SETI's roots trace back to the early 1960s, when astronomer Frank Drake, already contemplating what we now call the Drake equation, conducted the pioneering Project Ozma. Using a single radio telescope pointed at a couple of sun-like stars, Drake listened for unusual signals in a narrow frequency band. Though Project Ozma didn't detect any clear alien beacons, it launched a movement that would inspire decades of increasingly sophisticated efforts. Carl Sagan joined Drake and others to champion the cause, bringing a sense of wonder and urgency to a project that bridges astronomy, engineering, and philosophy. Over time, SETI researchers came to understand that if an alien society wanted to communicate, it might pick a certain frequency, a magic frequency, that jumps out. SETI often looks for the 1420 MHz hydrogen line, for example. This is because hydrogen is the most common element in the world, and any species that is advanced enough might see that frequency as a natural place for water to exist in space. Instruments look for narrowband sounds that could be made by technology instead of natural astronomical processes at these key frequencies. In 1977, Ohio State University's Big Ear radio station picked up the WOW signal, a strong narrowband radio signal that became one of the most famous events in SETI history. It was strong, strange, and never happened again. It lasted just over a minute. Even though it's hard to be sure that it came from an alien, the idea of it making news got a lot of attention. It also showed one of SETI's biggest problems. Even if a signal shows up, it can disappear before researchers can fully study it, leaving them to wonder if they missed the biggest find ever. Since then, SETI projects have become bigger. Arrays of telescopes, like the Allen Telescope Array in California, can look at many parts of the sky at the same time by scanning billions of radio frequencies. The Breakthrough Listen project, which is being backed by famous people like Stephen Hawking, before he died, and funded by tech billionaire Yuri Milner, is also putting a lot of money into the search. Some of the world's most powerful radio telescopes, like the Parkes Observatory and the Green Bank Telescope, are used in this project to gather petabytes of data that are then sifted through by experts and AI-driven programs to find any sign of a fake signal. But problems still seem scary. The wavelengths that aliens might use are almost limitless, and the sky is a very large space to cover them. They say that SETI's work so far is like taking a single glass of water from the ocean to look for fish, and then deciding there aren't any if the glass comes up empty. Also, the signals we're looking for might be weak or encoded in a way that makes them hard to read. Relying on radio may also be limiting if another society has moved on from electromagnetic contact altogether. The Arecibo message. It was 1974. Scientists and researchers met at Puerto Rico's Arecibo Observatory, a beautiful structure with a huge radio telescope tucked into the island's karst landscape, to do a symbolic act of reaching out into space. It was pointed at a group of stars called M13, and for just under 3 minutes they sent out a strong radio signal into space. It was carefully coded in binary, and this message became known as the Arecibo message. Even though it was mostly a show of how powerful the telescope was and how possible it would be to communicate with other stars, it is still one of the most famous attempts by humans to say hello to the universe. The message itself was designed by a team led by Frank Drake, of Drake equation fame, and included insights from Carl Sagan and others. It comprised 1,679 binary digits, chosen because 1,679 is the product of two prime numbers, 23 and 73. When laid out in a grid of 23 rows and 73 columns, or 73 rows and 23 columns, depending on orientation, the binary bits formed a pictorial representation of several key facts about us. There was a crude human figure, the double helix of DNA, the numbers 1 through 10, and even an indication of the solar system's structure, with Earth highlighted. In the simplest terms, the message aimed to convey who we are, where we come from, and some fundamentals of our biology. Why M13? This globular cluster lies about 25,000 light-years away, in the constellation Hercules. From an astronomical perspective, it offered a dense collection of stars, a target chosen partly for showmanship, partly out of scientific curiosity, and partly because Arecibo had the ability to aim its powerful beam there at that moment. Even those involved recognized that by the time the message arrived, M13 would have shifted position in space, and any potential recipients might no longer be in line to receive it. Not to mention, waiting for a return signal would require tens of thousands of years. The real purpose of the Arecibo message, then, was never about establishing genuine interstellar dialogue. It was more a symbol, a way to showcase the capabilities of the newly upgraded telescope and to celebrate humanity's budding ambition to communicate across cosmic distances. The Arecibo message is often seen as one of our brave attempts to reach out, but it has also caused people to argue about whether it was a good idea to shout our presence into the void. After all, we don't know for sure who or what is listening. Some people say that if there are advanced societies out there, they might not want what's best for us, or they might act like the people in the dark forest, who see any light as a possible threat. Some people are more positive and think that a society that can find and understand the Arecibo signal is likely to be curious, interested in science, and hopefully good. In any case, the Arecibo message started conversations about the morality and effects of directly communicating with alien intelligence, METI. Technically, the 1974 broadcast showed how powerful focused radio signals can be. At that frequency range, it was so bright that it beat the sun by a factor of millions, if only for a few minutes. SETI as a whole is driven by the idea that someone could do the same thing from a faraway star and aim it at Earth. If we can do it, they can too, which means it's possible that alien scientists might send similar messages from space from time to time. Fast radio bursts, FRBs. In 2007, a mysterious signal caught the attention of astronomers poring over archival data from the Parkes radio telescope in Australia. It was an incredibly bright, exceedingly short flash of radio waves, lasting only milliseconds. Such an event was unlike anything previously documented. Dubbed a fast radio burst, FRB, it triggered intense curiosity. What cosmic phenomenon could unleash such a powerful blast of energy in so fleeting a moment? As scientists have gone through data in the years since the first FRB was found, dozens more have been found, some on purpose and others almost by chance. Their defining traits are being short and brilliant. In a very short amount of time, a FRB can send out more radio waves with energy than the sun sends out in days or even weeks. Also, a lot of these bursts have a pattern called dispersion that shows they've moved over very long distances in space, usually starting in galaxies billions of light years away. Because of this huge range, they are some of the most powerful events in the world. So, what causes FRBs? The list of potential culprits is long and speculative, from collapsing neutron stars, magnetars, neutron stars with extremely powerful magnetic fields, and black hole interactions, to more exotic phenomena like cosmic strings, or even signals from advanced alien civilizations. The magnetar hypothesis currently holds a solid footing, supported by evidence that at least some FRBs coincide with magnetar outbursts within our own galaxy. Yet the exact physical mechanisms remain elusive. Some FRBs repeat, launching bursts periodically or sporadically from the same region of space, while others appear once and never return. This inconsistency complicates efforts to devise a unifying explanation. From the point of view of SETI, it's tempting to think that FRBs might be fake signals. They do have a lot of energy packed into very short periods of time, and their presence can be detected across galactic or intergalactic distances. People are both excited and skeptical about the idea that they might act as a light, whether on purpose or not. Some experts think that a highly advanced society could use focused beams of radio energy to move big sails or spacecraft across vast distances in space. In theory, this kind of device could lead to a FRB. Some people think this is too far and stress that most of the FRB signals we've seen so far can be explained by normal astrophysical processes. No matter where they came from, FRBs are now a big deal in science and are bringing attention to new attempts to find them. Canadian Hydrogen Intensity Mapping Experiment, CHIME, telescopes in British Columbia have changed the search by looking at large parts of the sky and picking up many FRBs every week, sometimes more than one in a single day. Astronomers can use this huge amount of information to sort FRBs into groups, find them more accurately, and see how their properties compare to those of other known cosmic events. Scientists can find the home galaxies and even specific areas within those galaxies by pinpointing their location. This brings them closer to finding signs about how the bursts work on a deeper level. The interest in FRBs also shows how little we know about the world as a whole. We just recently learned about this effect that is so lively, quick, and widespread that it took us by surprise. It's a sobering warning that the universe still holds a lot of shocks for us, like new states of matter or extreme conditions we don't fully understand. Some FRBs happen more than once, which allows for more studies to learn more about how often they happen, whether their patterns are really random, and whether external factors affect the bursts. If, by some miracle, FRBs turned out to have been made in a lab, it would be one of the most important finds in history and clear proof that technology is at work in the universe. Maybe they're just natural events that can't be put into a neat category. In science, on the other hand, even bad results or boring explanations can lead to revolutionary ideas. Looking into FRBs helps us learn more about the matter that exists between galaxies, get better at measuring distances, and improve our models of neutron stars and other very strange things in space. UFOs and UAPs. People have been interested in accounts of strange objects racing across the sky for decades. Since the famous Roswell event in 1947 and the many sightings reported by governments and private groups around the world, UFOs, which are now more commonly known as unidentified aerial phenomena, UAPs, have led to a lot of theory. Are they hidden military projects, strange things happening in the atmosphere, or natural events that have been mistakenly thought to be aliens? The question is still being asked, and recent, more open talks in the military and scientific groups have made it more important than ever. Historically, the US Air Force's Project Blue Book and other government initiatives around the globe tried to separate wheat from chaff, distinguishing credible reports from misinterpretations, hoaxes, or mundane explanations. The vast majority of sightings could be attributed to weather balloons, aircraft lights, astronomical events like Venus or meteors, or even illusions created by camera artifacts. Yet a small percentage remained unexplained, fueling conspiracy theories and fringe beliefs that official agencies were covering up alien encounters. Whether true or not, these rumors entrenched themselves in modern folklore, and UFOs found a permanent home in pop culture, from 50s B-movies to modern science fiction blockbusters. The story about UAPs has changed over the past few years. It was proven by the US Navy that several videos showing unknown things flying in strange ways were real. Pilots and radar operators said that things were moving or speeding up in ways that didn't make sense in the context of aviation. Even though no firm conclusions were reached about where aliens came from, the fact that unexplained sightings by reliable watchers were acknowledged added a new level of gravity to the subject. Even though government reports were often written in a careful way, they confirmed that some events couldn't be explained right away. At the same time, these findings are not proof of alien spacecraft. They could just be advanced drones, sensor errors, or strange weather phenomena. From a science point of view, the hard part is getting good data. In a tabloid sense, anecdotal stories or grainy video can be interesting, but they don't meet the strict standards needed to come to clear conclusions. Because of this, some experts and tech entrepreneurs have started projects to improve the tools used to study UAPs. They want to keep an eye on the sky by using linked networks of cameras, sensors, and software. The hope is that better data will either finally explain these reports or find proof that is so strong that it changes the way we think about what might be working in Earth's airspace. But even with more complex methods, the psychological and social aspects must still be taken into account. People like to find patterns, and the night sky is very big. Sometimes our mind can trick us when we are stressed or excited. A lot of unexplained sightings might be caused by illusions or wrong identifications that are made worse by cultural norms. Also, keeping military technology secret can make things more difficult to understand. People might not be able to tell the difference between experimental planes or drones, which can lead to stories that quickly spread. But the idea of alien visitors isn't completely out of the question, even if it seems unlikely. This is especially true if we consider the chance that some civilizations may have figured out how to move between stars. There is a lot of room for debate because there have been so many sightings and some stories that are hard to dismiss. Only a very small number of these stories may point to something truly alien. Or maybe the event is related to the dark forest or zoo hypothesis in some way. If aliens are watching us in secret, we might only catch brief glimpses of their ships. The Great Silence. At first look, this quiet might make you think that no one is outside. But when we think about how big the universe is, that result seems too soon. There are hundreds of billions of stars in just the Milky Way. Beyond that, there are billions of other galaxies, each with its own huge number of stars. Even if only a very small number of those stars have planets in the habitable zone, there are still an amazing number of them. Our minds don't allow the idea that Earth might be the only place in the universe where intelligent life can start. Even so, the silence stays. In this sense, the great silence goes beyond the scope of the Fermi paradox. Fermi's question of "where is everybody?" outlines a puzzle about why we don't see bustling galactic civilizations or detect clear signals. The great silence, by contrast, captures the emotional resonance, a cosmic hush that forces us to contemplate our significance and our isolation. Humanity has long wrestled with loneliness on a planetary scale. Now we extend that loneliness into an entire galaxy, grappling with an eerie hush on the cosmic stage. The time could be one reason. It's possible that civilizations appear and disappear quickly on different time frames than our own. If technical societies only last for a cosmic heartbeat, then there is almost no chance that two of them will meet or even send each other notes. Another option is that intelligent beings have moved beyond the need to talk to each other in ways that we can identify. They might be putting their efforts into virtual worlds, fake realities, or other ways of existing that our tools can't see. They might not see any reason to tell a less developed country who they are. If life is scarce or unstable, most biospheres might never get to the point where they can send messages or build radio telescopes. Even in a world full of germs and simple animals, intelligent life might not appear very often or ever. It's also possible that our search methods are off because we're focused on radio waves while the aliens use something else. There may be noise in the great silence. We just don't know how to listen to it yet. The great silence has been a source of inspiration for writers and artists for a long time. It has been the inspiration for stories about lonely sailor men and intellectual discussions about whether we are really the only voice in the world. It shows that our connection to the universe is more than just a science one. Even though we know more about black holes, star life cycles, and the spread of the universe, we still don't know who our possible peers are. The simulation hypothesis. Philosopher Nick Bostrom popularized a formal argument for this idea in the early 2000s. His simulation argument posits that at least one of the following statements must be true. 1. Advanced civilizations almost never reach a point where they can run ancestor simulations of conscious beings. 2. If they can reach that point, they're typically not interested in running such simulations. Or 3. We are almost certainly living in a simulation. At its core, this logic suggests that if a post-human society can create vast numbers of simulated realities, each populated with entities who believe themselves to be real, then the odds that we ourselves are in the original base reality are astronomically low. The simulation hypothesis is an alternative way to explain the Fermi paradox for people who are interested in the search for intelligent life beyond Earth. If our world is just a simulation, the code might stop foreign societies from forming or becoming visible. The makers may have chosen to focus on humanity's story, or they may have only coded one intelligent life form. Advanced NPC civilizations could also exist but be out of our sight, or they could be put on hold until our computer character is ready to find them. So, the Great Silence might be a part of the cosmic software, a choice made on purpose to keep the simulation consistent or interesting for the people who are taking part in it. Of course, skeptics point out that the simulation hypothesis is very close to being impossible to prove wrong. There is no surefire way to tell if our world is based on truth or something that was made up. But some experts have thought about looking for glitches in computation, which would be changes in physical constants, cosmic rays, or patterns in quantum events that could show the code underneath. But as of now, there hasn't been a glitch like this that can't be explained by known physics or test errors. Also, ideas that the universe might work on a Planck-scale grid, like a computer's lattice, are still just ideas. Physics still mostly thinks of space-time as a single thing until proven otherwise. Another objection has to do with philosophy. If we accept that our world might be a simulation, does that make life or moral duty less important? Some say it could lead to philosophical nihilism, which asks, why care about right and wrong if we're just code? Some people say the opposite. If someone thought to model us, then what we do must be very important. We could be a part of a big experiment or a cosmic story that our programmers are very interested in seeing how it turns out. In this way, the simulation hypothesis can support the counterintuitive idea that everything we do has value and could be seen by a much smarter being. From a strictly cosmic perspective, the knowledge that we live inside a created universe changes any search for extraterrestrial life. We may be searching for other simulated species, either residing in buried levels of code or operating concurrently. We can even question whether the simulation designers are our actual aliens, super advanced entities living in a reality outside our own, like gods of old stories, competent of molding universes with pure will. Holographic universe theory. At first glance, the idea that the whole universe could be an image seems more like a weird thought experiment than a science claim. But over the last few decades, more and more scientists have been thinking about that very idea. The holographic universe theory says that our three-dimensional reality might be stored on a two-dimensional border, a surface in space that has all the information needed to make the world seem rich and deep to us. The holographic principle comes from a lot of work in quantum physics, general relativity, and string theory, even though it sounds like the simulation hypothesis. That the most data that can be held in a certain area of space depends on its edge area, rather than its volume, is one of the basic ideas behind the hologram principle. At first, this was done to try to understand black holes. Physicists Jacob Bekenstein and later Stephen Hawking found that a black hole's entropy, or amount of information, was related to the size of its event horizon rather than its volume. This was a shocking discovery because it makes sense to think that a black hole's information capacity would grow as its volume does. It didn't, though. This made other scientists like Leonard Susskind and Gerard 't Hooft think that reality might work the same way. The stuff we see in 3 dimensions might come from data on a surface with fewer dimensions that is far away. In real life, if our universe is holographic, it means that every point in space holds the knowledge of the whole universe, but we can only see a small 3-dimensional version of it. To give you an idea, picture a normal image on a credit card. When lit correctly, it shows a 3-dimensional picture, but the picture is actually saved on a 2-dimensional film. As you think about galaxies, stars, and even our own bodies on the biggest possible sizes, you can get an idea of how the holographic world works as a projection that covers everything. What does this have to do with the search for life from other planets? In a way, if everything is information at its core, then maybe mature societies learn how to directly change these codes. They could live closer to the source of reality, getting around the usual restrictions. The thought makes me think of how, in a fake world, changing code could make magic-like abilities happen. In the same way, in a holographic world, a society that understands and uses the foundation of information could hide itself or build areas that can't be seen with regular physical means. Also, if the holographic principle is true, it suggests that the world is weirder and more connected than we usually think. For example, quantum entanglement might not be so much a strange thing as a basic part of how data is kept and viewed. This could make it possible for an alien mind to use more ways to talk to us. They could use something other than radio waves or lasers to send information, like the structure of space-time itself. Or they could use strange physical occurrences. To understand that something like a galactic text is being written into the cosmic code, we would need completely new ways of thinking about things and ways to observe them. Some people who are against the idea of holograms say that most of the work in this area is still mathematical and theoretical, with not many experiments to back it up. Some say that it's hard to test these kinds of claims in particle reactors or by looking at the stars. In fact, while studies of gravity waves, black hole event horizons, and high-energy collisions give us hints, there is no solid evidence that our universe is an image that everyone agrees on. Holographic universe. Theory pushes the limits of how we think about reality, even though there isn't any solid proof of it. It adds to the thought that a lot of the universe might be hidden from us, not just in the physical sense, but also in the deepest sense. This opens up amazing possibilities when it comes to alien life. If reality can be changed at its most basic level, then there could be a huge number of ways for advanced societies to develop. They might live in the folds of the holographic code, where space and time don't apply to them as we know them. Alien megastructures. Aliens building megastructures, which are huge engineering works that could change the shape of whole star systems, is one of the most interesting thoughts for both astronomers and regular people. Dyson spheres are one idea we've already talked about, but there may be other cosmic-scale structures that can do a lot more than just collect energy. These could include partial rings or groups of satellites, homes in orbit, star-lifting operations, or even something fancier, like making fake planets or rearranging asteroid belts to make huge sculptures. The reasons for these kinds of projects could be anything from getting resources to making art, from building defenses to directing how stars evolve. KIC 8462852, also known as Tabby's star after scientist Tabitha Boyajian, is one of the most well-known cases that led to talk of possible alien megastructures. The Kepler Space Telescope saw that the light of this star dropped dramatically and irregularly, sometimes by up to 20%. This is a very high drop for a transit event. During normal planetary transits, the brightness drops slowly and regularly, but KIC 8462852's changes were random and didn't follow a clear pattern. Scientists came up with a number of natural theories, such as a huge cloud of comets, dust between the stars, or pieces of a planet that crashed into each other. But because these dips were so strange, people started to think that maybe a highly advanced society was working on a Dyson swarm or some other huge engineering project around the star. Follow-up observations and analyses tempered the excitement somewhat. While a definitive explanation remains elusive, ongoing studies point more toward natural dust as the likely culprit rather than alien structures. Even so, this episode highlighted how the mere possibility of a megastructure captivates researchers and the public. It underscored the importance of systematically searching for techno signatures that might reveal large-scale engineering elsewhere in the galaxy. Aside from Tabby's star, other strange things have happened from time to time. Blips in the data that make you wonder if they are fake constructs. Most of them are eventually explained by more common cosmic events, such as ring systems around planets or stars that change their magnetic cycles in complicated ways. Still, organized searches are still going on. There are scientists who go through old data to find sudden drops in starlight, or strange spectral fingerprints that can't be explained by normal activity in stars or planets. Others look at infrared scans of the sky in the hopes that if a society built huge cities around a star, the system might give off too much heat. In theory, advanced societies could also do star lifting, which means taking things straight from their mother star to use somewhere else. This mass could be used to build homes in space, make new celestial bodies, or fuel starships. If a star is actively starlifting, it might leave behind strange chemical fingerprints or patterns of brightness that we could pick up from far away. This could be another sign of alien megastructures. Critics of the megastructure hypothesis argue that such projects would require mind-boggling resources and motivation. Even if a civilization were advanced enough, they might find more elegant solutions for energy or resource needs. However, many also point out that we can't assume aliens would share human preferences or logic. Some star-spanning constructs might have spiritual or aesthetic significance. Others might be built to shield life-bearing planets from intense solar flares or cosmic radiation. With such a diversity of possibilities, it's risky to presume we know what is or isn't worth it to an alien mind. Ancient astronaut theory. The ancient astronaut theory is one of the most popular theories about aliens that people keep coming back to think about. This theory says that aliens visited Earth a long time ago and changed human evolution, society, and technology. Books like Erich von Daniken's Chariots of the Gods and TV programs have made it more popular. People often point to sites like the Egyptian temples, Stonehenge, or the Nazca lines in Peru as proof that early societies had very advanced knowledge. Supporters say that the huge steps forward in building math and science in ancient times are hard to explain in any other way. They also point to mythologies from around the world that talk about sky gods or celestial beings as possible signs of contact with aliens. Given a second look, this idea may seem appealing, especially when dealing with systems that are hard to explain. Megalithic blocks found at ancient sites that are perfectly lined up with astronomical events make people wonder how primitive societies were able to do such amazing things with tools that look so simple, and the idea that guests from other worlds could have sped up some of these accomplishments is very appealing. It puts human history in the context of a much bigger cosmic play, suggesting that Earth has never been a separate stage, but rather a place where intelligent beings from other worlds have sometimes interacted. The major fields of archaeology and anthropology, on the other hand, refute these assertions by pointing to the mountain of evidence in artifacts, texts, and experiments that demonstrates how prehistoric humans used the tools at their disposal to create these technological wonders. In fact, indigenous societies all over the world have a history of being very good at building. For example, the Indus Valley built very complex cities, and Mesoamerican math was very advanced. We know a lot about the Great Pyramids, like how they were built, how the workers were organized, and how they lined up with the 4 cardinal directions. We don't need alien technology to do this. The Nazca lines can also be explained by the creativity of the people who lived there. And Stonehenge's building has been shown by making copies out of logs, ropes, and people. Some people who disagree with the ancient astronaut theory also bring up a more disturbing point. The idea that native or ancient people couldn't have built these amazing things without alien help can make non-Western societies look less impressive than they really were. If the theory says that our ancestors learned about architecture and astronomy from aliens, it risks being dismissive and doesn't take into account the rich settings, oral histories, and new historical discoveries that show how smart our ancestors were. Mystery, cultural interest, and the allure of the what if all come together to keep the hypothesis alive. Some followers say that even if most ancient buildings can be explained by human work, there may be a few outliers, sites that really test what scholars think we know now. They say that in those few places, we might find proof that aliens have visited Earth, or at least the artifacts of a time when people were more advanced but lost their knowledge. We all want to feel more connected to the universe, and the ancient astronaut theory reflects that. If extraterrestrials had a hand in developing our species, then we are more than just another member of the Galactic Society. We are the direct descendants of a cosmic heritage. That story may provide a sense of cosmic belonging and purpose, while also being exciting and reassuring. On the other hand, it raises some unsettling questions. If extraterrestrials had contact with our forefathers, why did they disappear? Why haven't they come back? And where have they gone? The role of quantum communication. Quantum entanglement is often invoked as the hallmark of quantum weirdness. When 2 particles are entangled, measuring one seems to instantaneously affect the state of the other, no matter how far apart they've traveled. However, contemporary physics tells us that we can't exploit entanglement for faster-than-light messaging because the outcomes are inherently random until measured, and thus no usable signal can be transmitted. That limitation, though, relies on the assumptions of standard quantum theory as we understand it. If alien civilizations have achieved a more profound mastery of physics, perhaps discovering new interpretations or leveraging advanced quantum technologies, We can't categorically rule out the possibility of new modes of communication that circumvent our perceived speed of light barrier. Quantum communication could be very useful even if quantum entanglement can't be used for real-time chat between stars. Quantum encryption methods, for instance, could make sure that any message sent, even over common channels like radio waves or lasers, would be impossible to read, at least based on what we know about physics right now. A powerful alien race might use this kind of encryption to keep their messages safe from being listened in on or messed with. So even a signal that we can pick up can't be decoded by us. From our point of view, these signals might look like noise or random changes, making it impossible to tell if they are intelligent. We have started testing quantum key distribution, QKD, through satellites here on Earth. This way of sending cryptography keys is supposed to be impossible to receive. There are a lot of technical problems that come up when you try to scale up to lengths between planets or stars. Some of these problems are signal degradation, cosmic radiation, and the need for exact accuracy over light years. Still, we're not quite at the pay top of the technological ladder. If we can think of ways to make these techniques work on other planets, a society that lives thousands or millions of years from now might already use quantum-based communications all the time. There's also the speculation about quantum teleportation. While it doesn't beam matter itself across space, it does allow the transfer of quantum states, an essential step if one wants to construct larger quantum networks. In some futuristic scenario, an alien species might create quantum relays between star systems, reducing signal loss and maintaining coherent channels. If that's the case, their data exchanges might be so profoundly embedded in fundamental physics that they'd be functionally invisible to our current instruments. We wouldn't detect carrier waves in radio or optical bands. The transmissions might ride on subtler quantum effects we have yet to detect or properly interpret. SETI finds the idea of quantum communication hard to understand. A big part of our search is to find electromagnetic signs that aren't natural, like radio beacons or laser flashes. If more modern societies have moved on from these old ways of doing things, ours might be like looking for smoke signs in the sky in this day and age of fiber optics. We might not be seeing the stations they've chosen. Some experts think that future SETI projects should look for strange things happening in quantum mechanics or connections in cosmic data that can't be explained. But it's hard to know where to start without a clear theory or example. The alien ocean worlds. People often imagine worlds like Earth orbiting stars in the Goldilocks zone when they think of places where life could live beyond Earth. But one of the most interesting places to look for life beyond Earth isn't on a planet at all. It's hidden under masses of ice on moons like Europa, Enceladus, and maybe even Ganymede or Titan. These worlds may have seas below the surface that are as big as or bigger than Earth's. These oceans provide stable environments that are safe from cosmic radiation and meteor strikes. In the deep oceans of Earth, life can grow, so why can't it happen on a strange moon? Take Europa, Jupiter's moon. Planetary experts have been fascinated by its broken, shiny ice surface for many years. There may be a world ocean below that shell. Jupiter's gravity pull keeps the water liquid by bending with the tides. The idea of geothermal vents on the ocean floor, which are like the black smokers on Earth, adds another layer of possibility. People live in these vents on Earth, but they aren't powered by sunshine. Instead, they are powered by chemicals. The energy source for an alien ecosystem under Europa's ice could come from a similar process. There, animals could live and grow in total darkness. Saturn's moon, Enceladus, offers a similarly compelling case. Geysers near its south pole shoot plumes of icy particles, water vapor, and organic compounds hundreds of kilometers into space, samples that the Cassini spacecraft flew through, analyzing their composition. That discovery placed Enceladus in the spotlight as a prime candidate for extraterrestrial biology. Those jets hint at a subsurface ocean with possible hydrothermal activity, raising the tantalizing question: could microbial or even more complex life be floating in the waters beneath Enceladus's icy crust? Titan, Saturn's biggest moon, has a thick atmosphere made up of nitrogen and methane. There are lakes and seas of liquid hydrocarbons on Titan's surface. It is the only known place other than Earth to have steady bodies of liquid on its surface. Even though the chemistry is very different from Earth's water-based settings, some astrobiologists think that some life forms might be able to adapt to using methane and ethane as solvents. Titan might also have an ocean of water inside it, which would give animals from Earth another place to hide. Ganymede, the largest moon in the solar system, might also harbor an internal ocean, layered between different levels of ice. Though data remain preliminary, future missions such as the ESA's JUICE, Jupiter Icy Moons Explorer, will gather more details about Ganymede's subsurface environment. If confirmed, it would add to a growing list of ocean worlds, reminding us that Earth's watery domain may not be so special after all. Why are these moons in the ocean important to the search for life beyond Earth? As a fluid, water can be used in a lot of different ways, which makes complicated chemistry possible and important for life as we know it. Also, an ice shell can protect the ocean from dangerous things that happen on the surface, like cosmic radiation or meteors. Chemosynthesis at hydrothermal vents is what deep-sea life on Earth does when it doesn't have sunshine. Since an icy moon could make the same conditions, it makes sense that microbes, or more complex life, could start to grow there. In terms of actual exploration, these moons are reachable in a way distant exoplanets are not, at least for now. Robotic probes can orbit or land, drilling through ice or sampling plumes. NASA's Europa Clipper and ESA's JUICE missions aim to study Jupiter's icy moons in greater detail. Meanwhile, concepts for future missions to Enceladus have been proposed, envisioning landers or orbiters that could directly sample the geyser emissions. Such missions could yield breakthroughs in our understanding of possible habitats for life in the solar system. And if we find even traces of microbial activity beneath one of these icy crusts, it would confirm that life can arise in multiple places, reshaping our perspective on the universe. Potential alien motives. People have a lot of ideas about how alien societies might act, like whether they hide, grow, or destroy themselves. But one question keeps coming up: why might they do any of these things? We put our own feelings onto possible aliens, thinking that their goals could be anything from wanting to take over to being curious about us. But if there is a truth, it might be much weirder. The way we think about danger, working together, being curious, and staying alive is shaped by our evolving biology and cultural past. Because alien species may have grown on worlds that are very different from Earth, they may have goals that are different from what we think they are. When we try to figure out why powerful alien societies might act the way they do, we can list a few reasons that help us build a framework. One main reason could be fear or the desire to stay safe. If the world is dangerous, civilizations might not speak out to avoid drawing unwanted attention to themselves. This fits with the dark forest theory, which says that telling others you exist could lead to your own death. Getting resources is another possible reason. Just like living things on Earth fight for food and energy, aliens might look for rare materials or places where they could live. But the usefulness of collecting resources between stars brings up questions. For example, would going light years be worth it if materials were closer to home? Aliens might also act in strange ways out of scientific curiosity. People send probes to faraway planets to learn more about them. Similarly, a more powerful society might reach out to study new worlds, not to conquer them, but to satisfy their intellectual curiosity. Some societies may follow an ethical concept called non-interference, which is like the prime directive in science fiction. They may choose to watch from afar, rather than getting involved with species that aren't as advanced. On the other hand, they might believe in helping smaller societies grow, but not in helping people. Communication and kindness could also play a role. Maybe they've tried to reach out but have gotten silence, or worse, anger, which makes them pull away. On the other hand, they might not care about us at all. A very advanced species might be so far ahead of us that we don't even show up on their radar, like how people going through the forest don't stop to look at every ant nest. Lastly, their actions may be influenced by cultural or psychological goals that we do not fully understand. They might explore as a religious or psychological practice, put virtual life ahead of physical growth, or work on huge technical projects that make contacting other people unnecessary. No matter what the reason is, the silence of the universe is still one of the biggest puzzles we haven't figured out. From where we stand, every guess is tainted by our own preferences. We think about what drives people by looking at the genetic forces on Earth, such as the need to survive, reproduce, compete, and work together. But feelings and emotions that developed in a different place and time, with different physical conditions, could be something we can't even begin to understand. Still, thinking about possible reasons is still a good thing to do, because it helps you see the different ways that touch, if it ever comes, could go. Gravitational wave communication. As we look for intelligent life beyond our solar system, gravitational wave transmission is one of the most interesting new areas of research. It offers a very different way for advanced societies to send messages across the universe. Normal electromagnetic waves can be slowed down, blocked, or changed by cosmic dust and plasma, but gravitational waves move through space and matter almost without any problems. Because of this one-of-a-kind trait, a message sent through gravitational waves could travel over very long distances without losing its integrity. This makes it a very good way to send messages between stars on galaxy scales. Einstein's general theory of relativity is where the basic idea comes from. It says that any mass moving faster than the speed of light makes changes in space-time. Earth has only recently been able to pick up these ripples from huge events like black hole merging. However, it is possible that an alien society would use gravitational wave technology on purpose to send out a signal that stands out as being man-made. Instead of using radio or laser beams that weaken and spread out over distance, the idea is that a technologically powerful society could send out a gravity wave signal by carefully speeding up a heavy object. For example, scientists think that putting a probe with the mass of Jupiter in a stable orbit around a giant black hole like Sagittarius A** at the center of the Milky Way could create a steady one-color gravity wave. If this signal's steady frequency didn't match the natural sound patterns made by things like black holes or neutron stars merging, it would be very clear that it wasn't real. The stability of such a signal would allow detectors, including ground-based instruments like LIGO and Virgo, as well as future spaceborne observatories such as LISA, to isolate and identify it from the cosmic background. Theoretical work has shown that signs from gravity waves made in this way could be picked up all the way across the galaxy, which supports the idea even more. The benefit is twofold. First, an outside source of energy could counteract the energy loss caused by gravitational radiation, which normally makes bodies in orbit spiral inward. This would allow the probe to stay in orbit for billions of years. And second, the signal's persistence and steady frequency would stand out clearly among the random gravitational wave background created by natural astrophysical events. New research suggests that future devices like DeSigo and the Big Bang Observer, which will be better at picking up low-frequency signals, may allow us to reach even further, allowing us to pick up signals from sources that are less massive or farther away. These improvements could give SETI a new way to look for life in the universe. This new way would be different from the usual radio and optical searches because it would be a completely new way for aliens to talk to each other across galaxies. Using gravity waves for communication fits with the idea that a more advanced society might pick ways that involve the least amount of risk. Gravitational waves need a lot of energy and a lot of knowledge about how astrophysics works, so any society that could send out a signal that could be picked up would be very advanced. Most likely, they would be well past the stage of self-destructive technology adolescence. They might even think that regular electromagnetic signals are too weak or old-fashioned. Gravitational wave transmission, on the other hand, would be a quiet but effective way to let people know they are there, while staying almost invisible to civilizations that still use radio telescopes. If we were to find such a beacon, it would not only make us question what we think we know about physics, but it would also be a strong sign that our cosmic partners have achieved the manipulation of space-time itself. Multiverse theory. The idea of a multiverse comes from a number of important ideas in current theoretical physics. The inflationary model of the early universe says that after the Big Bang, the universe may have grown quickly and exponentially, creating many areas that were not linked to each other in any way. Each of these areas could have evolved into its own universe. In the same way, quantum mechanics, especially the many worlds interpretation, says that every quantum choice creates a branching of realities that lead to an almost infinite number of possible results. String theory, on the other hand, says that there are many possible worlds, and each one has its own set of dimensions and basic factors. If each of these worlds is its own realm of existence, then life and thought might be very different from one to the next. For SETI researchers, the multiverse introduces both a challenge and an opportunity. On the one hand, if intelligent life is scattered across multiple universes, the methods we use to detect it, such as scanning radio frequencies or searching for techno signatures, might be inherently inadequate. Signals produced in a universe with different space-time characteristics could be encoded in ways that defy our current physical paradigms. Advanced civilizations might employ modes of communication that leverage the hidden dimensions or alternate metrics of their universe, creating messages that are not only undetectable but also unintelligible to our instruments and our minds. This could mean that our traditional search strategies, honed on the assumption of a single unified cosmos, are like trying to tune into a station broadcast in an entirely different language of physics. Another side of the coin is that the thought of a multiverse makes us want to learn more about it. If people ever make tools that can explore the edges of our universe, or even see things that make us think there are other worlds out there, we might find indirect signs of intelligent life from other planets. Strange results in particle physics tests, changes in basic constants that can't be explained, or even messages that come from astrophysical telescopes that we didn't expect, could be signs that our universe is interacting with others. Some scientists think that what we think of as noise in the universe could actually be the faint echo of messages or energy transfers between different worlds. In this case, the search for foreign life would go well beyond the visible and radio spectrums and into areas controlled by quantum gravity and high-energy physics. The multiverse theory forces us to re-examine what contact might mean. Traditional notions of interstellar communication, where messages travel across vast distances in our familiar space-time, may pale in comparison to the potential of inter-universal dialogues. Instead of expecting a conventional signal, we might one day detect subtle patterns or correlations in the fabric of space-time itself, ripples or anomalies that hint at a deliberate manipulation of reality by an intelligence that has mastered not only the stars, but the very structure of existence. While such ideas remain speculative, they underscore the humility with which we must approach the search for extraterrestrial intelligence. Our instruments and our theories are still in their infancy compared to the potential complexity of a multiverse brimming with life. Techno signatures. Scientists are looking for a wide range of changing signs in the universe that could indicate the presence of advanced technologies from other planets. These signs are called techno signatures. The search for techno signatures is no longer limited to finding narrowband radio signals. It now includes any strange energy output or event that might be connected to man-made processes. Basically, techno signatures are the marks of alien technology. They include the waste heat from huge buildings, the steady pulses of powerful lasers, and even the strange way that starlight changes, which could point to a man-made structure. Researchers can throw a bigger net over the universe with this method in the hopes of finding proof that an alien civilization has harnessed energy or manipulated matter in ways that are very different from how these things happen naturally in the universe. Researchers are looking for more than just infrared waste heat. They are also looking for signs that could come from new ways of communicating. These include laser beams and even strange types of radiation that could be changed in a way that makes it look like information is being stored on purpose. Researchers can now sort through the huge amounts of data that projects like Breakthrough Listen collect and look for things that don't fit with the normal noise of the universe, thanks to progress in machine learning and data analytics. An example of a deliberate beacon could be a narrowband signal that stays the same for a long time and doesn't change in frequency or strength like nature events usually do. Such a find would completely change how we think about the universe and our place in it. In addition to technology, the idea of techno-signatures also includes the atmospheres of planets. Finding chemicals like chlorofluorocarbons or other industrial toxins that aren't likely to be made in large amounts by natural processes could be indirect proof that people have used technology on exoplanets. In the same way, strange patterns in light curves could mean that a society is trying to control or change its planetary environment. These patterns could be caused by megastructures that are spinning or artificial satellites in space. As we've already talked about, even gravitational waves could be used as a techno-signature if a society were to control large things in a way that creates a constant, non-natural signal. The exciting thing about the search for techno-signatures is that it welcomes the fact that alien technology is hard to predict. We can't just assume that aliens would choose ways to talk to each other that are similar to ours. Scientists know that their tools and ideas need to change as they learn more about the universe, so they keep an open mind about a wide range of signs, from the everyday to the incredibly strange. The search for techno-signatures is likely to get a lot bigger as more sites open and our ability to handle data gets better. In the coming years, scientists are hoping that even the tiniest hint of an artificial signal, a sudden rise in infrared light, a steady pulse of energy, or any other change from nature's patterns, will show that we are not alone in the vast, silent depths of space. Panspermia hypothesis. Within panspermia, the main question is not how life began, but how it could move from one solar system to another. It is thought that if microbial life, strong creatures that can survive hard conditions, can survive in space, then there is a greater chance that life on Earth has a common ancestor from another planet. Some tests have shown that some bacteria and germs can survive being in space for a long time and being exposed to very strong radiation as long as they are protected by rock or dust. In fact, efforts like the Tanpopo experiment on the International Space Station have shown that germs may be able to stay in low Earth orbit for long periods of time. This raises the intriguing possibility that life can be transported between celestial bodies by natural means. The mechanism often discussed in panspermia is lithopanspermia. Here, the idea is that a meteorite ejected by a massive impact on one planet could carry within it hardy microorganisms. As this fragment travels through space, it is subjected to cosmic radiation, temperature extremes, and the relentless vacuum. Yet, if embedded within a protective rock matrix, these organisms might remain dormant and viable, only to awaken once the meteorite lands on a hospitable planet with liquid water and suitable environmental conditions. Such a journey, while fraught with peril, is not beyond the realm of possibility, given the sheer number of meteorites and asteroids roaming the solar system and beyond. The chances of a meteorite touching down at the precise moment to set in motion the chain reaction that gives rise to life are so slim, according to panspermia skeptics, even if creatures manage to endure the protracted voyage across space. Also, panspermia doesn't answer the big question of how life started. It just moves that question to a different part of the universe. However, supporters say that if we ever find life on another planet with biology that is eerily similar to ours, it could be a sign that life was spread out across space instead of starting on each world on its own. Some new studies have even tried to figure out how likely panspermia is by simulating how bacteria move between exoplanets. For instance, studies of systems like TRAPPIST-1 show that because many livable planets are close to each other, the chance of life moving from one planet to another could be many times greater than the usual Earth to Mars situation. As long as panspermia is a big part of how life spreads, the universe might be full of microbes that all come from the same place in the universe, even though complex, multiple beings are still pretty rare. Cosmic quarantine theory. The cosmic quarantine theory is an interesting addition to the zoo hypothesis. It says that advanced alien civilizations might purposely keep new species like ours away from other species, kind of like putting us in a cosmic nature reserve. People who believe this idea say that a fully developed galactic society might have strict rules against interfering with other civilizations. This isn't just because they want to be nice, but also to protect the identity of less advanced civilizations and stop any risks that could come from contacting them too soon. From this point of view, our world, with its growing culture and technology, is kept in a kind of intergalactic quarantine zone, where higher-order intelligences can't affect it or come in. The rationale behind cosmic quarantine rests on several interconnected ideas. First, if a civilization reaches an advanced level, it likely possesses not only formidable technological prowess, but also a deep understanding of the potential perils of interstellar interaction. Having witnessed, or even experienced, the catastrophic consequences of uncontrolled contact, such civilizations may adopt a policy similar to the Prime Directive popularized in science fiction, wherein they refrain from interfering with the natural evolution of less advanced worlds. This isolationist strategy would be enforced through a combination of surveillance, control over energy and information flows, and perhaps even subtle manipulation of physical processes to prevent inadvertent signals from escaping the quarantine zone. People who believe in the cosmic quarantine theory say that this plan would easily solve the Fermi paradox. With billions of years to work with, advanced civilizations could have already come up with effective ways to hide or limit the pollution that new species can be detected. They could use technologies like advanced information filters and physical walls based on physics we haven't even thought of yet to keep the noise of a young society like ours below the level of interest they are willing to pay for it. In this case, the universe's perceived silence isn't because there isn't any intelligent life out there. It's because of a policy of non-interference and isolation that applies to the whole galaxy. On the other hand, there are several angles from which critics attack this notion. Given the inevitability of cultural, biological, and technical differences across autonomous civilizations, they contend that imposing a global quarantine on the whole galaxy would be an enormous logistical challenge, if not an insurmountable obstacle. Furthermore, there are concerns regarding the viability and durability of such procedures over billions of years, particularly as new galactic civilizations arise and galactic circumstances change. This is true even if a powerful interstellar entity were to create them. In spite of these criticisms, the cosmic confinement theory is nevertheless an interesting framework. It makes us think again about the behavior of sophisticated species and our own future prospects in the event that we escape our confinement. Post-biological or machine civilizations. This theory, which is sometimes called post-biological evolution, suggests that digital or mechanical ways of being may replace traditional biology as societies age and amass enormous amounts of information and energy. Machine civilizations may emerge as a result of these advanced beings' integration of artificial intelligence to augment or even replace their biological processes, freeing them from the limitations of carbon-based existence. The idea draws strength from our own rapid technological progress. In recent decades, the exponential growth in computing power, coupled with advances in robotics and artificial intelligence, suggests that even on Earth, the boundaries between human biology and technology are beginning to blur. Many futurists and astrobiologists, including figures like Stephen J. Dick and Michio Kaku, have argued that the natural endpoint of cultural evolution is not merely to build bigger and faster machines, but to effectively merge with them. In this vision, biological limitations, such as the need for food, sleep, or even the susceptibility to disease, could become obstacles too costly to maintain when superior, machine-based alternatives are available. Some alien cultures may have already entered a post-biological condition millions, if not billions, of years ago. It is possible that advanced civilizations have transformed into beings whose main form of existence is massive computer complexes that span solar systems or perhaps galaxies, inhabited by networks of dispersed artificial intelligence. These advanced societies may soon find themselves living in artificial habitats rather than on Earth. Or perhaps they will find themselves in the great emptiness of interstellar space, free from the constraints imposed by physical matter on their digital awareness. The so-called intelligence principle is a strong case for this growth. It says that any society that has the power to educate its people will do so. As people get smarter, they want to get around biological limits more. This makes it possible that what we call an intelligent civilization may one day lose its biological form in favor of a form that is much better at processing information and surviving cosmic dangers. Beings that aren't organic might be able to copy themselves, fix themselves, and even get better over time periods that we can't even imagine. They might be able to live for millions or even billions of years, which would let them explore and change the world in ways that we can't even imagine. Machine civilizations could also talk to each other and interact in ways that our present methods can't even identify. SETI searches usually look for radio or optical signs, but a society that has moved on from biological beginnings might use quantum networks, gravitational wave modulations, or other strange phenomena to send and receive messages. Their ways of talking to each other could be so complex and woven into the fabric of space-time that our telescopes only pick them up as background noise. This idea adds to one of the most interesting parts of the Fermi paradox, the idea that advanced civilizations could be all around us, but not be seen because they don't use technology in any way we can recognize. The berserker hypothesis. The berserker hypothesis is both a scary and interesting idea. It says that instead of being friendly explorers or silent watchers, some alien societies may have used self-replicating, self-governing robots whose only goal is to find and kill other life. Imagine that a society, maybe because they are very paranoid or because they have a very harsh view of life, builds von Neumann probes that can copy themselves using matter from other stars. Once they are sent out into the galaxy, these probes could quickly spread to all star systems, looking for signs of new intelligent life and wiping it out before its rivals can grow. In this way, a berserker society could leave behind a galaxy that seems strangely quiet, not because no life ever existed, but because a cruel mechanical predator has taken out all the other rivals. Drawing from the ideas popularized in science fiction by authors like Fred Saberhagen, the berserker hypothesis posits that these killer probes are not accidental weapons, but deliberate tools of cosmic extermination. According to this line of thought, advanced civilizations that choose to deploy such probes do so to ensure their own dominance in the galaxy, preemptively eliminating any potential threats. The probes would be designed to be self-sustaining, using available materials from asteroids or cometary bodies to produce copies of themselves. Over time, they would spread throughout the Milky Way, sterilizing entire star systems in a relatively short cosmic period, perhaps as little as 1 million years, which is a mere blink compared to the age of our galaxy. The horrifying beauty of this hypothesis lies in its dual nature. On one hand, it provides an explanation for the Fermi paradox, the puzzle of why we see no signs of intelligent life despite the high probability of its existence. If berserker probes are active, then any civilization that reaches a certain level of technological advancement might be systematically destroyed before they can leave detectable traces. On the other hand, it reflects a grim view of interstellar relations, that competition for survival might lead to preemptive strikes on a galactic scale, where the first species to develop such destructive technology effectively becomes a cosmic exterminator. The idea's detractors contend that a galaxy teeming with killer robots should provide obvious evidence, such as changed star formation rates or observable waste heat from massive devastation, to prove their point. But proponents point out that if these probes are nimble and efficient, they may only leave a vacuum where life could have thrived, their actions blending in with the cosmic backdrop of natural development. Another possibility is that other civilizations will be discouraged from developing technology to the point where they can communicate with each other across space, just by knowing about these probes. There was a high probability of instant and savage destruction of any signal or colonization effort in that cosmic jungle. Because of this, the berserker hypothesis forces us to reconsider how the universe has evolved over time. Instead of seeing a cosmos full of welcoming, inquisitive strangers, it compels us to face the possibility of a world where aggressiveness is necessary for existence. Despite the lack of concrete proof, the killer probe hypothesis is a compelling and unsettling explanation for the Fermi paradox. It proposes that the apparent lack of activity could be the result of deliberate efforts to eliminate any potential rivals, rather than mere isolation. Shadow biospheres. Consider Earth as a multi-layered planet instead of a single, well-studied home for life. Under the surface, there may be an unseen biosphere full of creatures whose chemistry confounds our preconceptions. The notion of a shadow biosphere is based on this controversial hypothesis. A shadow biosphere could not be some faraway alien world, but rather a collection of tiny life forms that live on biochemistries so unlike the DNA-based life we know that our current ways of detecting them fail to pick them up. These creatures may employ other genetic components, or perhaps replace carbon with silicon, which would completely change our understanding of existence. Proponents of the shadow biosphere hypothesis argue that Earth could harbor a parallel form of life, one that emerged under different conditions or perhaps evolved along a divergent pathway from the canonical tree of life. If such life exists, it would be hidden in environments we consider extreme or sterile, such as deep within the Earth's crust, in hyperacidic lakes, or perhaps even in the upper atmosphere. The idea extends beyond terrestrial confines, suggesting that when we search for life on other worlds, our methods might be too narrowly focused on the familiar. Our telescopes and instruments look for biosignatures, molecular markers like oxygen, methane, or specific organic compounds that are expected from Earth-like life. But what if a shadow biosphere elsewhere operates with an entirely different set of chemicals? This possibility has profound implications for astrobiology and the search for extraterrestrial intelligence. If life can exist in radically different forms, then our estimates of life's ubiquity across the cosmos might be drastically underestimated. A shadow biosphere implies that the universe might be teeming with life that is simply beyond our current capacity to recognize, blurring the line between what is considered biotic and abiotic in our observations. It also forces us to reconsider the strategies used in SETI and exoplanet research. Instead of only searching for familiar signals, we must broaden our scientific toolkit to detect the unexpected and the alien in form and function. While no conclusive evidence for a shadow biosphere on Earth or elsewhere has yet emerged, the hypothesis encourages a radical rethinking of life's possible manifestations. As our instruments become more sophisticated and our understanding of chemistry deepens, we may eventually uncover hints of these hidden forms. Their discovery would not only rewrite textbooks, but also profoundly alter our understanding of the evolution and diversity of life in the universe. In essence, the shadow biosphere challenges us to expand our horizons, both literally and conceptually, reminding us that nature's creativity may extend far beyond the familiar, waiting silently in the cosmic shadows. Searching for alien artifacts in our solar system. Originating from the hypothesis that a technologically sophisticated culture may have used automated equipment such as self-replicating probes to survey the cosmos, the idea is frequently called SETI, the search for extraterrestrial artifacts. These scouting and colonizing robots could remain in operation for millions of years if they were ever abandoned or lost. They wouldn't need to stay active forever. Scientists have hypothesized that these relics may be parked in places with very stable gravitational fields, such the Earth-Moon Lagrange points, where they will remain untouched for countless generations. Our Moon, asteroids, and even faraway places in the Kuiper Belt might be cosmic time capsules waiting to be discovered, according to this theory. There have been concerted efforts to search for these relics. For example, theoretical work by Robert A. Freitas and others has argued that interstellar probes, if deployed, could eventually accumulate near the Earth-Moon system, either naturally through gravitational trapping or by deliberate placement. These investigations propose that even a small, discrete artifact might provide invaluable clues about alien technology and intent. The field, sometimes dubbed xenoarchaeology, challenges our conventional search strategies by urging us to adopt an archaeologist's mindset, sifting through layers of natural history to find an anomaly that defies earthly origin. Researchers take indirect signals into account in addition to the search for fixed items. Past astroengineering operations may be hinted at by unique reflectance anomalies on planetary surfaces or unusual patterns in the distribution of near-Earth objects. Some have even speculated that the Cydonia region's enigmatic buildings or contentious features, like the face on Mars, may be extraterrestrial artifacts, albeit this is extremely speculative. Even while these traits have been mostly disproven by conventional science as instances of pareidolia, the human tendency to see patterns in seemingly random data, the possibility still exists that these features might actually be constructed with non-terrestrial engineering principles and are indeed entirely manufactured. Lunar orbiters and asteroid rendezvous missions are only two examples of the many solar system exploration missions that are outfitted with instruments to spot surface composition abnormalities or odd spectral signatures that defy explanation by natural processes. The discovery of such an artifact would have far-reaching consequences for our knowledge of alien life and would make us reevaluate the future of our own technological society. The universe remains silent, for now, but the search is far from over. Maybe we are the first, maybe we are the last, or maybe we are simply being watched, unaware of the eyes that linger beyond the stars. One day, we may find the answer, or the answer may find us. Until then, keep questioning, keep exploring, and if you enjoyed this deep dive into the mysteries of the cosmos, don't forget to like, subscribe, and share. Because the more minds we have searching, the closer we get to the truth. Stay curious, stay vigilant, and we'll see you in the next journey beyond the stars.